Okay, welcome back to probability modeling. Today we should be finishing what we have to say about Poisson processes. So let me first start by a quick reminder of what we did last time. So we basically extended the definition of the Poisson process to include Poisson processes with variable rates. And the most important thing to remember with the variable rate is that assumption A is slightly changed. So now NUV is not Poisson with parameter lambda times the length of the interval UV. Instead, it's the integral of the rate lambda over this interval. Apart from that, things are the same. So there's no need to worry. And yeah, so we had a few things and an example, but yeah, just remember definition A change the length of the interval by the integral of the rate over this interval. Then we talked about superposition, marking, and thinning. So superposition is just that when you add two independent Poisson processes, then you get a new Poisson process with rates being the sum of the rates of both the first ones. So you can add up independent Poisson processes, but the independence assumption is crucial, so don't forget that. And marking is basically the reverse. So you take a Poisson process, and then each time there's an event, assume that this event comes with some extra random information in form of a random mark. So you're given mark A, type A with probability PA. And then we have this theorem about marking, which says that each of the marked processes, so the process where you only count events with a specific type, they're also Poisson, and they're independent from each other. And the new rate is just the old rate times the probability of being of the mark you chose. So it's really the reverse of superposition. Superposition is you can add independent Poisson processes, and marking is you can split one into multiple independent others just by choosing their types independently at random. And there's also thinning, which is just a special case where we only remember one of the types. And so your new rate is P times lambda. Okay, so that's in short what we did last time. Now let us move on to, we have three sections to do today. The first one is conditioning on the number of occurrences in an interval. So this is a section really just to mention one specific, very nice theorem. So we go back to the constant rate. So just have a Poisson process with rate lambda. And if we condition by the number of occurrences in, let's say, the interval 0t, could be any interval, but let's say we condition by having n occurrences on the interval 0t. Basically, your interval 0t has n points inside. Let me actually, just to be clear, so if I have my interval 0 to t here, and so I've conditioned my Poisson process to have n occurrences. So, maybe I'll mark them with crosses. Maybe they happen like that. Maybe n equals 4. And my Poisson process happens to have 4 occurrences. So 2 of them are pretty close, but things are random. Then the theorem says that, in fact, these 4 crosses I've put on my interval, they have the same distribution as if I had taken 4 independent uniform variables on my interval 0t, and then plot the 4 on my little graph here. Conditionally on having n occurrences on the interval 0t, these n occurrences, their positions, are distributed like a sample of uniform distributions, which is very nice. Maybe it's not so surprising. So it means that the Poisson process, it's very nice and regular and homogeneous in a way. So let's say if you have a Poisson process of a bus arriving, and someone tells you the bus arrived between 1 p.m. and 3 p.m., then, assuming the Poisson assumption is correct, then the position when exactly that bus arrived is actually uniform between 1 p.m. and 3 p.m. We don't have any extra information. Okay, let's give this a shot. Try proving this. So the first thing is, so what exactly do we mean by having these points distributed as a random sample of uniform? So when there's 1, it's clear. When there's 4, it's a bit less clear. And we're going to interpret this like that. We're going to say that, so we're conditioning on having n occurrences in my interval 0t. And then the number of occurrences which occur in a smaller interval, uv, this should have a binomial distribution. And the parameter should be n tries, and the probability of any try being successful is v minus u over t. Maybe now is a good time to go back to paper. So I'm saying, if I have my interval again, and I chose a small interval, so let's say everything which happens between here and here, u and v. So you can see the length of this is about a bit more than half of the total length of the interval. Let's say that t is 1, because it's simpler, and that the length of this here, v minus u, is L. L looks to be more than half. So if I take a uniform variable, the probability of it landing here is L, of course. So if I take n of them, I will get a binomial with parameters n, L, which land inside. So this is how we're going to interpret as our set of points is distributed as n independent uniforms. And so let's go on and actually prove this. Proof. So let us prove. So wait, let me give you the number of the theorem. Theorem 23. Proof of theorem 23. And so we will show that conditionally let's put like this, conditionally on n 0t equals n, the distribution of n uv is binomial n v minus u over t, where I've chosen 2 arbitrary u smaller than v. Okay. And to make things simpler, I'm going to let, just as I did just earlier, L is the length of v minus u, because this will get written a few times. Okay, so how do I do this? Well, remember what's going on in the Poisson process. The total number of events happening between 0 and t, let's go back to t instead of 1, is a Poisson variable. And those who land inside this smaller interval is a smaller Poisson variable. And the difference between the two is, of course, what happens here plus what happens here. But we know the distribution of all of these. So nuv is Poisson, nvt is Poisson, and n0u is also Poisson. So we can actually compute things directly. And to do that, I'm going to let x is n0u plus nvt, which is the same thing as n0t minus nuv, of course. It's what's on the side. By the definition of a Poisson process, so let's say by properties A and B, of a Poisson process, we get that x follows a distribution Poisson with parameter t minus L, and there's a lambda because there's always a lambda. Okay, why is it t minus L? Because here we have a Poisson with parameter u, here we have a Poisson with parameter t minus v. So really, we have, when we add both of those, we get the Poisson with parameter length of that plus length of that. Of course, that's the length which is not between u and v, so that's exactly t minus L. And nuv, I will remind ourselves that it's Poisson of parameter lambda L, and nuv is independent of x. Well, x and nuv are independent. And this is all the information we need now. So I'm going to let a be an integer between 0 and n. So let's say like that. A is 0, 1, ... n. And what is the probability that nuv equals a conditionally on n0t equals n? As we said, we want nuv to be binomial, so we want to get a choose n, a choose n times this to the power a times 1 minus this to the power 1 minus a. So how do we do this? Well, it's the usual first definition. So it's equal to the probability that nuv equals a and n0t equals n divided by the probability that n0t equals n. So this intersection isn't nice because these two events are not independent. nuv is not independent of n0t. nuv is independent of x. But of course, since this is the sum of nuv and x, we can just write this the other way. So this is probability that nuv equals a and x is n minus a divided by probability that n0t equals n. And now we can actually do everything because these things are independent, so we can write our product. So let's remind ourselves of how to write probabilities of a Poisson variable. And so we get, so it's going to be a big fraction, get ready. So this is lambda times L to the power a divided by factorial of a. So should put brackets like this, and then there's exponential of minus lambda L. This one's going to be the same, but replace L by t minus L, and n and a by a minus a, so we get lambda t minus L to the power n minus a divided by factorial of n minus a times exponential of minus lambda t t minus L. And we are left with this one, same thing, it's a Poisson, and let's squeeze it to the right, so it's in the denominator, so things get inverted, factorial of n, e to the minus lambda t, times lambda t to the n. Okay, and now just look at what happens. We should get exactly what we want. So first, notice there's a binomial coefficient here. Am I still on the webcam like this? So equals. So binomial coefficient, that's exactly n, choose A. What about the powers of lambda? There's a lambda to the A lambda to the n minus A, and then a lambda to the n. So the powers of lambda disappear. What about the exponentials? E to the minus lambda L, e to the minus lambda t minus L. So these, when multiplied, they becomes e to the minus lambda t, which disappears with that. And so we're left with just L to the power A, t minus L to the power n minus A. Not quite, because we have this division by t to the n here. And so you should put L over t here. And so this is divided by t, so let's put it as 1 divided by L over t. And now we're done. So I did most of the steps orally, because it's better than writing down everything, but I hope you got this. So we had t minus L to the power n minus A. I divided this by t to the power n minus A, so we're left with 1 minus L over t to this power. And of course, this is exactly what we want. This is what we want, the binomial bin and t L over t distribution. Excellent. That's what we wanted. Okay, this may remind you of the proof of what we did with marking. And yes, that makes sense, but because again, we're kind of splitting a Poisson variable n0t into two variables, nuv and x, and this is done through a binomial choice thing. So this is actually very, very much related to marking. Instead, the mark is whether we're in between uv or not. All right, let us go back to the slides. So, proof of this theorem is done. So actually, this theorem has a version with variable rate, which you should know as well. So, in the case of a variable rate, so if I condition my Poisson process to have n occurrences between 0 and t, then they're not going to be uniformly distributed. Instead, they will have this distribution, which is lambda of s as the density divided by the total integral of lambda between 0 and t. So what does that mean? It's the distribution with density proportional to the rate of the process, which makes sense. So if I told you that buses were way more common around 12 than around midnight, and I told you exactly one bus arrived that day, then it would be more likely that that bus arrived around noon than around midnight. So that's the idea behind this. So the number of occurrences in the interval uv is now binomial, but with this thing. So instead of length divided by t, replace length by the integral of lambda over the interval uv, and replace t, which was the total length, by the integral of lambda over the total interval. So it's really similar. Replace any length by the integral of the rate over the corresponding interval. And the proof will be very similar, so let's not do it. So it's just that now your nuv and your x are Poisson with slightly different parameters, mostly given by this thing, of course. All right, but we will do one example for this theorem, for the variable case, actually. So let me give you that. Example number 36. Example 36. So we do this thing where we condition on the number of events. So I'm going to take an arbitrary Poisson process with parameter lambda of t, which is equal to a plus b cosine of 2 pi t. Completely arbitrary. Let's take a bigger than b positive. In particular, lambda is not 0. Lambda is strictly positive for all t. And the question is, given that a Poisson process with rate lambda of t has three occurrences in 0, 1, what is the probability that these occurrences were actually all between 1/4 and 3/4? What is the probability that they all occurred in 1/4, 3/4? Okay, here's a question, and remember, we know that conditionally on this thing, so n equals 3, then the number which occurred in here is a binomial variable with parameters 3 and then this ratio of 2 integrals. So we just need to find out what is the probability that such a binomial variable is equal to 3. Yeah. So, 2 integrals to think of. What's the integral from 1/4 to 3/4 of a plus b cosine of 2 pi t dt? Well, we get half of a plus minus, no, plus, plus b times sine of 2 pi times 3/4 minus sine of 2 pi over 4. equals half of a plus b. So sine of 3 halves, sine of 3 halves, that's -1. And then sine of pi over 2, that's -1 again. So we get half of a minus 2b, and obviously I did something wrong. Because we forgot to divide by 2 pi. Hey. So b over 2 pi. And now we're good. Remember how to do your integrals, kids. Okay, so that's one thing. And the other, which is going to be easier, the other integral is integral from 0 to 1 of a plus b cos of 2 pi t dt. And this one is just equal to a. Because I guess this is something you should know, but when you integrate a cosine over the whole period, you always end up with 0. Okay. So now the wanted probability is the probability that 3 times we land in the interval 1/4, 3/4. So it's, remember, we have 3 independent variables whose density, okay, we have a binomial variable with parameter of success being that divided by that. And we want the success to happen 3 times. So the wanted probability is half of a minus b over 2 pi divided by a cubed. Or you can rewrite it maybe more nicely as half minus b over 2a pi cubed. Sorry, the 2's go away because I let's not forget to simplify this. It's b over pi, not b over 2 pi. Okay, so that's an example. So you have 3 points. You know that their density is proportional to a plus b cosine 2 pi t. So the probability that they land inside is the ratio of this integral and that integral. Since the 3 points are independent when we condition, we just cube this. So you should write by independence. Just in case. Not just in case. Explain where this cube comes from. All right. So we're done with this conditioning on the number of events happening. And really, yeah, we're done with that. But we can use it to build the Poisson process. So as I said before, we mentioned last time that we didn't technically build the Poisson process. And I told you that in the case of the constant rate, we could build it using the fact that the holding times, the interoccurrence times, were exponential. in the case of a variable rate, the interoccurrence times are not exponential. So it's not so easy to build it, but here's one way of building it. We can use this conditioning thing. So here's how you can simulate a Poisson process if you like. First, with variable parameter. First, split your whole real line. Let's say we want the Poisson process going for all times up to infinity. Split it into n minus 1 n for each n. So intervals of length 1, 0, 1, 1, 2, 2, 3, 3, 4, and so on. So we know that on each of those, if I choose 1 n minus 1 n, the total number of events which will happen inside is a Poisson variable with parameter the integral between n minus 1 and n of the rate. So call that xn. That's the number of occurrences between n minus 1 and n. And then we just need to place them exactly at the spots where we want them to be. And now that we know the behavior conditionally on the number of occurrences, this is easy. So if xn is 0, we know that there's none. And if xn has a positive value x is an integer, then just take x independent variables with this density. Remember, density is the rate, and then proportional to the rate. So you divide by the rate's integral over the integral we're interested in. And then these values will give us exactly where we want to be. So maybe I can again do a little bit of a drawing. So here's my real line. I divide it into 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, and so on. On each of those, I have my rate lambda. On each of those, I choose a Poisson variable with total parameter the integral of the rate on this interval. So let's say maybe x1 equals 0, x2 equals 0, but x3 was equal to 2. So I have 2 points I need to put in here. And I choose 2 points with density proportional to the rate. For it to be a density, the integral has to be 1. So we divide the rate by its integral. And this gives us the proper density. Then maybe I land here and here. Then maybe x4 equals 1. So I need to put 1 point here, chosen with density proportional to the rate between 3 and 4, so maybe it lands here, and so on and so forth. So one thing to be careful, though, is that we're assuming that this integral doesn't pose any problems. So this integral has to be finite. And that's fair. Like you can suppose that we only take Poisson processes with integrals being finite on finite intervals. Otherwise, things get weird. And this is not what we're interested in. And yeah, so it's not to show, by kind of reverse engineering all the proofs we've done, that this builds the variable rate Poisson process that we want. So great. Next, so here's a new section. We're done with the usual Poisson process and its variable rate version. Now we want to consider something which we call here the spatial Poisson process. So what's going on here? Well, we want to replace our time scale by something a bit more general like space. And so instead of saying that events happen at certain times, we will say that events happen at certain places. So your space can be one-dimensional. So let's say if we want to look at defects happening on a cable, if you model your cable as a one-dimensional piece of space and then take a Poisson process on it, well, one-dimensional space is kind of the same as time. But if we have more dimensions, then it's really a different beast. So 2 dimensions, yes. Positions of spots of rain on the pavement, this can be a Poisson process. or positions of stars in space can even be a Poisson process. So we want to create a more general definition. So you remember, of course, that a big feature of a Poisson process is that we use the length of time intervals to say that the number of occurrences happening inside an interval is Poisson with parameter its length times lambda. So here we need to generalize length in multiple dimensions, and you know, of course, that you can generalize length as the area in 2 dimensions or the volume in 3 dimensions. So there's even more in more dimensions. So in maths, we call this, in general, length, area, volume, as we call it measure. And we're going to write it like this. Absolute value of A is the measure of A. So if A is an interval, that's the length. If A is, say, a circle, that's its area, pi times radius squared. And if it's a piece of 3-dimensional space, then it would be its volume. And so we can define a Poisson process with a parameter lambda. So we can call it density, since it's not time but space, that kind of makes sense. It's the average density of points happening. So we're going to have our variables n. So we're going to call them n of a. N of a is like n of uv before. N of a is the number of occurrences of points which land inside a set A. So you can view your Poisson process as just throwing a bunch of points in space. N of A is the number of points which fall inside my set A. And here are my assumptions 1 and 2, which are the same as A and B before, to define my spatial Poisson process. And here they are. So as before, the number of points which are inside a specific set A is a Poisson variable, and its parameter is lambda times measure of A. And if I take disjoint sets A1, A2, AK, then the points landing in each one of those are independent as well. So this is really the simplest way you can think of generalizing things. It's basically the same, but lengths are replaced by measures. And everything, well, not everything, but the definition really works as before. Things fit properly because we have the additivity property. So if I take 2 sets which don't intersect, I can add up the corresponding Poisson variables, and I'll get a Poisson variable with bigger parameter because of independence. And yes, most of the things generalize. For example, we can superpose. So if you add up 2 independent spatial Poisson processes, you get a spatial Poisson process, and its rate, it's the sum. We can mark things by saying that each point actually comes with an additional mark, and it's marked with type I, probability pi, and same thing. If we split the big Poisson process into smaller ones, they are indeed Poisson processes, and they're independent. The new parameters are lambda times the probability of having the mark we're looking at. And we can do the conditioning thing we just did. So if I know that there are n points in the box A, and if I take a smaller box B inside A, then the number of points inside B will be binomial, and its parameters will be n, the number of tries, and size of B divided by size of A for the probability of success. And we're going to see that very soon with an example. So we're not going to prove anything because the proofs are the same. It's always, well, we have some Poisson variables and they are independent and we can add them together, or we can split them with binomial marking, and so on. There are no differences at all. Here's a simulation. So this is what I said before. Now I have two-dimensional space, x and y, and I just throw some points inside. And what happens if I take any box, let's say a box like this, then the number of points which landed inside happens to be 3, was a Poisson variable with parameter the area of this box. And you can take the total box, so from 0 to 1, this has area 1, so the total number of points landing inside, I'm not going to count them, is a Poisson variable. Its parameter is the area times lambda. I forgot to say times lambda. There's always a parameter lambda somewhere, because we can have this freedom. Okay, so there's one thing which doesn't generalize, and it's the interoccurrence time. Sorry, we're having the slides in small. We should have them in big. Here's the big picture. So the interoccurrence times, these things don't generalize because you can't really talk about a point and the next point and the next point. Now, in one dimension, the occurrences are naturally ordered. There's the first, there's the second, there's the third. In more dimensions, it's less natural. Like, if you ask me what's a good way of calling the first occurrence, well, it's not very nice, right? There would be ways of doing it. You could say, for example, sort them just with their x coordinates, in which case you'd have the first one here, second one here, third one here, fourth one here, and you could get information. But this is kind of arbitrary, because we could sort them by the y coordinate, or we could sort them by their distance to the origin, or anything. And indeed, in some cases, you would get exponential variables in some senses, but it's not worth building a theory around that. So we don't talk about interoccurrence times. However, the idea used in the proof of the interoccurrence time can be useful. For example, the distribution of the distance to the nearest point from a given point. And I think we have an example around that. Yep, this is the final example of the course. Example 37, distance to the nearest tree. Give me a sec. So, example 37, distance to a nearest tree. So, suppose that we have a forest, and this forest is actually a Poisson process in 2 dimensions. Suppose the positions of the trees in a forest are given by a spatial Poisson process. Could call this SPP with intensity lambda. And we're going to do 2 questions. The first one is not the distance to the nearest tree, really. Let's be more clear before the questions, though, is that we're taking our forest to be the whole plane, r squared, and so we're putting points according to this Poisson process. And say the number of points occurring in anything, for example, this squiggly box is a Poisson variable with parameter equals to the area which I circled here. Okay, so here are my questions. A, given that there are 3 trees within 10 meters of a given point, so okay, I chose this point here, so a given point is arbitrary. There's 3 trees within 10 meters. Suppose that these 3 x's are all within 10 meters of the point I chose. What is the probability that they are actually within 5 meters? 5 meters. And this is something we know how to do because, so we have a circle of radius 10 which has 3 trees inside, and so the question is, look at the small circle with radius 5. What's the probability that it has 3 trees? Well, we know that the number of trees inside the smaller circle is binomial. So let's say A is the disk with radius 10, and B equals disk, the same origin, same center of the disk with radius 5. And the question we want is probability that n of B equals 3, conditionally on n of A equals 3. And that's the probability that a binomial with parameter something is equal to 3. And the something is the ratio of the areas. Remember, we had ratios of the lengths. Here we're saying that if a point lands inside the big disk, then it's uniform inside this big disk. So the probability that it lands to the smaller one is the ratio of the areas. And remember the area of a disk, that's pi times 5 squared here, so pi times 25, divided by pi times 10, so pi times 100, and this gets cubed. Okay, so 1/4, so we get 1/4 cubed. So the example which is given in the PDF is a different one. The one given in the PDF is what's the probability that none of them are inside this. Let's do this as well. So that's was what I wrote here, but that's not necessarily what was asked somewhere else. So just for completeness, what is probability that n of B equals 0 conditionally on n of A equals 3? Well, that is going to be, of course, so we know the ratio of the areas is 1/4, so it's going to be 1 minus 1/4 cubed, and that's 27th out of 64. That's two questions around the same thing here. The probability that a binomial is 3, here the probability that a binomial is 0. Okay, part B. Actually, to make it complete, so either they are or none are. There you go. Part B, which is what the subtitle was about. Find the density of a certain random variable of R, which is the distance of a given point to its nearest tree. And this uses similar ideas, as we said, to the interoccurrence times. So find the density. To do that, what is often good is to say that the density is a derivative of the distribution function. So we look for the distribution function first. Look for the distribution function. So probability that R is smaller than or equal to R. So that's the probability that I have my given point, and then I take a circle with radius R, and I want at least one point inside this. And we know that the number of points inside is a Poisson variable, and its parameter is the area. So we're going to need more paper. But this is equal to 1 minus exponential of minus lambda pi r squared, because pi r squared is the area, and this is the probability of a Poisson variable being 0. So 1 minus this is the probability that the Poisson variable is at least 1. And so the density is a derivative, of course. So the PDF probability density function of R is the derivative so the derivative of that is 2R exponential of minus lambda pi R squared. Okay. And now we're good. So why is this like interoccurrence times? So you may remember for the interoccurrence times, let's say for the first one, we said, what's the probability that the first interoccurrence time is smaller than little t? Is the probability that at least one point is inside not a circle, but an interval of length t. So we did the same thing, and instead of having pi r squared here, we just had t. And then we said, well, this is the exponential variable. Here, it's something else, of course. Okay. This may actually be the end of that section. No, one more thing. So, again, we can use variable rates also in spatial Poisson processes. And again, it's the same thing. Replace the measure of anything by the integral of the rate function over your space. So the number of points landing inside a box A is the integral of the rate inside this box A. And again, just as in the usual Poisson process, any mention of length was replaced by an integral. Here, any mention of area, volume, or measure is replaced by an integral, and things generalize completely fine. And so the reason we want to use variable rates is because they can model more things. It's more general, more powerful modeling tool. Especially, we can model clustered behavior. So sometimes points may just happen to land, many points may happen to land close to each other for biological reasons, if you want. And while if the rate was constant, then things would be pretty irregular. Some effects can be modeled with regular, as in non-varying rates. Some things, because of this clustering property, may need variable rate. For example, well, here's a simulation. So here's your usual 2D Poisson process, and here's something with more clustering. So clearly you have a rate which is pretty high in this region, that region, and this region, and seems to be, well, even then these guys are quite close. So even then maybe the rate is clustered, is high around these points, and then the rate is very low everywhere else. Okay, and so this ends what I want to say about spatial Poisson process. So lengths are replaced by areas or volumes. That's really all you need to know. Apart from that, it works similarly, and remember, interarrival times don't quite exist. So we're done with the course. We're just left with this thing, which is a bonus and won't be the exam. Compound Poisson process. So if you're curious, you can keep on listening. But now things are strictly optional. So let me talk you through this a little bit. Sometimes the Poisson process is nice, but we want to increase its modeling power through a different way, which is by giving a numerical value to your events. For example, I'm an insurance company, and I'm interested not only in knowing when insurance claims happen, but I want to know what the size of my insurance claim is. If people want for more money, for less money, that's also interesting. I don't just want to know when this happens. Or maybe something not money related, but if you model your road accidents, you may want to know not just when or where an accident happens, which is a usual Poisson, spatial Poisson things, but also know how many people died in that accident. This lets you model different things and sort things differently. And turns out this is not too hard. So what you can do is you can take your times of occurrences to be your usual Poisson process, and then say that at each occurring event, you have an extra random variable. And that these have the same distribution and are independent of each other and of the time at which this happens. And this is what we call compound Poisson process. So actually quite simple. So n of t is n0t. So remember, I told you before that it's often denoted as n0 as n of t. So that's the number of events occurring before 0t. And then I'm given these variables y1, y2, y3, which are the sizes of my occurrences. And I define this new interesting random variable, x of t, is the sum of the yi's for y smaller than n of t, basically. This is what you call the compound Poisson process. And the best way is to think of it graphically. So let's first look at the graphic here. So this may remind you of the graphs of n of t we saw before, but here, as you can see, the jumps have different sizes. So before, we always jumped upwards with a jump size of 1. Here, the jump size is my random variable y1 here, y2 here, y3 here, y4 here, and so on. However, the jump times, they are the times of my Poisson process. So we can write here. You can plot, both nt and xt together if you like. So nt, it jumps by 1 at each occurrence. Well, xt jumps by the random quantities y1, y2, and so on. So here, xt jumps upward, but it doesn't have to be the case. If my y has a distribution which can be negative, then my xt can jump downwards. That's completely fine. And you'll notice that the distribution of this process is completely described by first lambda. So lambda will describe the Poisson process of where the events happen, and then what is the common distribution of these IID variables y1, y2, and so on. Because we know when we jump, and we know by how much we jump. So we know everything. So we get this interesting random variable xt. Now, I don't want to say much about xt itself. It has some nice properties. Law of large numbers happens, and some other interesting things. But other things we can also do is make this variable rate or make it spatial. So you could want to model locations of nests of birds and things like that. And then, so the place where you have the nests is a spatial Poisson process, and on top of that, you can add extra random variables, which would describe, say, the number of eggs and so on. And you can use a variable rate, as we said before, to model clustering, have some places with more spots than other places. But if we want, the number of eggs, the number of offspring raised by a parent, then the compound spatial Poisson model may be very useful. And that is all. Okay, so as I said, this was extra. It won't show up on any work you need to do, so no need to worry about that. So we're done with the course. So next Friday is a day off. And after that, I haven't decided yet, but I think I will go through an old exam so that I can show you properly what's expected of you. But all the skills you require are basically shown in the exercises. So if you understand the whole exercise sheets, you will be ready for the exam. The exam itself, so it's going to be an online test on Blackboard, probably 1 hour long. Things still have to be specified. But if I can, I will try and upload some kind of fake exam so that you have a good idea of how those questions work. But in any case, the questions won't actually be very different from what you know. It's just that you won't have to write much maths at all, and mostly you will be just selecting answers. So no problem about that. I should mention that there's an archive of past papers. You probably know that. It's linked to from the course homepage. There's papers from 2014 onwards. They are all good. They're all good practice papers, so feel free to look at any of those. And yeah, that's about it. So I'll announce early enough what I do next Tuesday. maybe an old exam. That's the most likely thing. And if you have any questions, I'm still here. No office hour on Friday because it's a day off, but you can send me emails or use the message boards. They work. All right, so I will see you next time.